Okay. So the definition of a symmetric matrix is pretty easy. A is symmetric if A equals A transpose. So that's actually one of the easiest definitions we've come across. So remember, A transpose flips all the columns of the rows. So that means if A is a matrix and you flip it along this diagonal, then you get the same matrix. Yeah, so it's pretty easy just to check by inspection if a matrix is symmetric. You just look at it and flip, all the rows should be all the columns and so forth. Okay, so what's important about these? Well, it kind of brings together two concepts we've talked about in the last few weeks. So two big concepts we've talked about were diagonalizability and orthogonality. All right, so we said, if you're given a matrix A, and you want to think about this, A is a matrix, is a n by n matrix, and maybe you want to think about this as a linear transformation, then maybe you want to find a basis for that linear transformation so that, a basis for the vector space so that the linear transformation is diagonal. And so diagonalizing A is finding a basis of eigenvectors. Because then when you write the linear transformation in that basis, you get a diagonal matrix. Okay, so this is just kind of some review. And then we also said, bases are nice. They let you describe an arbitrary vector space as a concrete vector space, Rn. But some bases are better than others. Some bases are better than others, right? And we said, which ones are better? Orthogonal bases are nice because, what's a nice property of orthogonal bases? Well, any vector can be written as a linear combination of your basis elements. So you need to solve some linear system to do that. But for orthogonal bases, you don't need to solve a linear system because you can just take dot products. So because if you want to write, let's say you have a vector y equal to like C1, B1, maybe B1 and through Bn are your orthogonal basis, then you don't need to solve a linear system. Right, you just take dot products. So orthogonal bases are really nice. You can do computations a lot faster. And bases of eigenvectors are really nice. And we know how to go from an arbitrary basis to an orthogonal basis. You do Graham-Schmidt. But what about matrices with an orthogonal basis of eigenvectors? What do we combine the two? Right? So some matrices have a basis of eigenvectors. But not every matrix has a basis of orthogonal eigenvectors. Because you might think, okay, what if we just take a matrix that has a basis of eigenvectors, and then we just perform Graham-Schmidt on those eigenvectors? Then we would get an orthogonal basis. But what you end up getting is not necessarily an eigenvector anymore. When you do Graham-Schmidt on a set of eigenvectors, you may not get eigenvectors back. You just get some other orthogonal basis. And so what matrices have an orthogonal basis of eigenvectors? That's the question we're dealing with? And the answer is symmetric matrices. And that's a spectral theorem. So let's write that out. Theorem. Let's see. Let A be an n by n matrix. Then A is symmetric if and only if. So both directions are true. If and only if what we say is A is orthogonally diagonalizable. And what that means is there is P and D is diagonal. Such that A equals P, D, P transpose. Sorry, P should be, there's P orthogonal and D diagonal, such that A equals P, D, P transpose is a P. Right, so notice that this is, we say is A is orthogonally diagonalizable. It means it's diagonalizable, but not only that, when you diagonalize it, its eigenvectors are orthogonal, i.e. A is diagonalizable, with an orthogonal basis of eigenvectors. Right, because right here, this is saying exactly, since P is orthogonal, P transpose equals P inverse. So this is exactly saying that A equals P D P inverse. And actually, and since P is the matrix that consists of your eigenvectors, we're saying those eigenvectors are orthogonal. Okay. So maybe a quick question. If A is symmetric, is A invertible? Just a warm-up question, maybe. And the answer? No, of course not. Right? If A is symmetric, it's orthogonally diagonalizable, but just because it's orthogonally diagonalizable doesn't mean it needs to be invertible. We've already gone over the fact that diagonalizable matrices don't need to be invertible. Right, here's an example. We just take any matrix that's symmetric that has eigenvalue 0. So let's take example, this matrix. This is a perfectly good matrix. Or even you could take the 1 by 1, 0 matrix. Right, this is symmetric. It's orthogonally diagonalizable, but it's not invertible. How do we orthogonally diagonalize this? Well, what are the eigenvalues? They're both 0. The eigenvectors for this are, well, anything in R2. The eigenvectors for 0 are, the eigenspace for 0 is all of R2. So we could just take 2 eigenvectors that are orthogonal. This is an orthogonal diagonalization of A. But it's not symmetric. Okay. And just so we get an idea of why this is true, let's just prove part of this. I'll do proof in quotes, it'll be a little informal. If A is symmetric, then eigenvectors, so I think this is done in lecture, but I'll just go over it again. Eigenvectors for different eigenvalues are orthogonal. This is what we're going to prove. Okay, so what we're going to look at is, let's say, let V be an eigenvector of A with eigenvalue lambda. And let's let W be an eigenvector of A with eigenvalue, let's say, mu. And let's look at AV dot W. This is just like a classic proof that you're going to see over and over again. Kind of proves a lot of things. So it's just nice to see the trick, right? So on one side, so I'm actually going to move this over here. On one side, you can do AV, you can rewrite that as lambda V dot W. But on the other side, you can write this as V transpose A transpose W, which you can write as V dot A transpose W. But because A is symmetric, this is V dot AW. And by the same logic as over here, we get it's mu V dot W. I just pull the mu out. And so you get that these two are equal, and this implies that mu must equal lambda. But let's say if we assume, V dot W equals 0. I guess these could be 0, or mu and lambda could be the same, right? But if we assume that these are not equal from the beginning, then this case is precluded, and so you get that the eigenvectors are orthogonal. So this is really the special thing about symmetric matrices, right? So if you imagine diagonalizing a normal matrix, you have your Rn maybe, which I'm going to draw as R3, right? And you have your eigenspaces. Maybe your first eigenspace is like a line. That's a line because of the origin. Maybe your second eigenspace is like a plane. It's like a plane somewhere. In general, these don't have to be orthogonal spaces to each other, right? But if A is symmetric, what we're saying is that these in fact are orthogonal spaces, right? If A is symmetric, this is supposed to be a line. It's a very fat line now. Then we're saying that this has to be orthogonal. Must be orthogonal if A is symmetric. On the left, did you read the dot product? Yeah. This is the definition. I think maybe you're talking about here or here. Okay, these are definition of dot products. You take a vector dot another vector, it's the transpose of that times W. That's the same as this. So any questions on what's going on right now? So if we give you a question, something like this, let's say we give you a question, let A equal 2, 4, 4, 2. Orthogonally, and I say orthogonally diagonalize A. What that means is you just want to diagonalize A, and then your eigenvectors, you just want to make sure they're all orthogonal. And so I just kind of made up this one randomly. What are the eigenvectors for this? Lambda minus 2 squared. It's 12. Okay, okay, yeah, sure. Let's just do this one. Okay, so determinant. I'll just do this one a little quickly. Get the determinant of 2 minus lambda 4, 4, 2 minus lambda. which equals okay. So 6 and -2. So you find your eigenvectors. Minus 4, 4, 4, minus 4. You get that 1, 1 is an eigenvector. Then you get 4, 4, 4, 4. You get 1, -1 is an eigenvector. Okay, and so to orthogonally diagonalize, we just need to make sure that these are orthogonal, but they're always going to be orthogonal if they're in different eigenspaces. So this one's actually pretty easy since it's a 2x2 matrix. We want you to, when you diagonalize it, it's just automatically going to be orthogonally diagonalizable. But let's say we do a harder example where this is a 3x3 matrix. So I'm just going to do another page. Let's say I give you a question that's something like, let A be, and I give you a 3x3 matrix. I don't know, I'm just going to make up some things. I'll just do this. I don't know if this is easy or not. And I say orthogonally diagonalize A, or explain why it's not orthogonally diagonalizable. Well, we know it's a symmetric, so it's automatically orthogonally diagonalizable. But now you might have to do a little extra work at the end because I don't know the eigenvalues are of this just yet, but let's suppose there are 2 eigenvalues. One has geometric multiplicity 2, and one has geometric multiplicity 1. So it is diagonalizable, right? And so now you have kind of so you have a span of 2 vectors here, v1 and v2, and this is a span of 1 vector, I don't know, w, right? And we know that since it's asymmetric, you know that w dot v1 equals 0, and you know that w dot v2 equals 0. Right, but you don't know that v1 dot v2 are equal to 0. And so if you want to orthogonally diagonalize, you need to actually Graham-Schmidt the first eigenspace. What's the difference between geometric and algebraic multiplicity again? The geometric multiplicity is a dimension of the eigenspace. Right, geometric multiplicity is dimension of eigenspace. It's the thing that matters when you want to know if things are diagonalizable. You want the dimensions of the eigenspaces to all be add up to n. So if there were 2 eigenvalues, for example, then you would have some 2-dimensional eigenspace, and so you would need to Graham-Schmidt to get orthogonal basis. And that's how you would actually orthogonal. So maybe we should actually do this. I don't know if this is a good example. Let's see if maybe this has an easy this one might be a little hard to find the eigenvalues. Maybe I'll save this one for later because it involves factoring this big characteristic polynomial. So we'll do this one for later. Because now let's talk about, I want to switch topics a little and talk about SVD. But maybe before I do that, are there any questions on what it means to orthogonally diagonalize? And I'll just reiterate what it means again as you're thinking about it. It just means that to orthogonally diagonalize, it means to write matrix as P, D, P transpose, where P is orthogonal, consisting of eigenvectors, and D is diagonal. How do you know w dot v1 equals w dot v2 equals 0? Well, that's what we proved. We know these are true because these are different eigenspaces. W is in a different eigenspace than v1 and v2. And so their dot products are 0. That was proven way back here. If you have eigenvectors of different eigenvalues, they're not equal, then you know that they're orthogonal. So that's why we get that these are orthogonal. Right, yeah. So to answer Haley's question, if we know that W is orthogonal to V1 and W is orthogonal to V2, but we don't know V1 and V2 are orthogonal to each other. And so if you just tried to do P equal to V1, V2, and W, this would be wrong. Because W is orthogonal to V2, W is orthogonal to V1, but V1 and V2 are not orthogonal. So this is not an orthogonal matrix. Yes, Graham-Schmidt proves that there are eigenvectors corresponding to the same eigenvalue that are orthogonal. You can always do that for any matrix. Come back to the page before this. Yeah, sure. There's, for any matrix, eigenvectors of the same eigenspace can always be made orthogonal. But the real question is, what about eigenvectors between different eigenspaces? Those are not always orthogonal. Yeah, V1 could be orthogonal to V2, but it's not guaranteed. So you should Graham-Schmidt it, the space to make sure that these are actually orthogonal to each other. And you could do that for any matrix. You could always just take an eigenspace and perform Graham-Schmidt on the eigenspace, and then you get some eigenvectors. The page, sure. Then you just get all your eigenspaces separately consists of orthogonal vectors, but it doesn't form an orthogonal basis because not the vectors between eigenspaces may not be orthogonal. That's only true if you're symmetric. Can I say that again? Yeah, sure. So what I'm saying is that for any matrix, let's say A is n by n, let's say not necessarily symmetric, then what you could do is when you, let's say it's also, let's say it's diagonalizable. Then what you could do is you can write A as P, D, P inverse, and let's say that you have some eigenvectors. Let's say the first three, I'm going to write a bunch of ones here. Let's say that the first three are in one eigenspace. And maybe the next two are in another eigenspace. And maybe the last whatever are in a different eigenspace, other eigenspaces. Then if A is an n by matrix, just any matrix that's diagonalizable, you could always just, one can always perform Graham-Schmidt on those eigenspaces. Can always perform Graham-Schmidt on each eigenspace separately. And what that would do is it would give you orthogonal eigenvectors within each eigenspace to get, let's say, W1, W3, and maybe W4 and W5, and then some more, so that W1 through W3 are orthogonal, so that these are orthogonal, and maybe these are orthogonal, and then the rest are orthogonal as well. You can always do this, but this doesn't orthogonally diagonalize A. because this is not an orthogonal basis. But this is not an orthogonal basis of eigenvectors because eigenvectors between different eigenspaces are not necessarily orthogonal. Because eigenvectors, that's the thing that still you can't do. Between eigenspaces are not orthogonal. Right, W3 and W4 are not orthogonal, i.e. W3 and W4 not necessarily orthogonal, right? And the thing that really makes this true, the thing that really makes eigenvectors between eigenspaces orthogonal, necessarily orthogonal, is symmetric. You need the matrix to be symmetric for everything between different eigenspaces to be orthogonal, because that's the thing you're missing in a normal matrix. Okay, so to orthogonally, just to sum up, to orthogonally diagonalize a matrix, first of all, it needs to be symmetric, and then all you need to do is just normally diagonalize the matrix, and then just make sure your eigenspaces within, are actually so you just need to make sure that eigenvectors within each eigenspace are actually orthogonal. Just complete the proof that if A is symmetric, it is orthogonally diagonalizable. Well, yes and no. If you assume that it's diagonalizable, then it completes the proof that it's orthogonally diagonalizable. But I don't think we've technically proven that if a matrix is symmetric, then it's actually diagonalizable, because that's part of the theorem. That not only is there's kind of two parts to this theorem, which is it's diagonalizable, and it's diagonalizable with orthogonal basis of eigenvectors. So we proved that over here, kind of this whole thing is saying that if it's diagonalizable, then it's orthogonally diagonalizable, if we assume symmetric. But we didn't actually prove that it was diagonalizable to begin with. And that's not something we're going to do, at least in this section. Yeah, the spectral theorem is actually like, as we've written it in this class, is actually just a very special case of a broader spectral theorem that kind of goes a lot more beyond just real finite matrices. It kind of covers complex matrices. It covers infinite dimensional transformations, or transformations between infinite dimensional spaces. So it's a lot broader, and that's not something we're gonna. This is just a precursor to all of that. Okay, so why don't we talk about singular value decomposition? I'm going to go to the next page. So kind of switching topics, kind of just a little. I mean, it still talks about symmetric matrices. Let's talk about SVD. So singular value decomposition. So this actually, like linear regression, singular value decomposition actually has a lot of real world applications. One of its main uses is to kind of compress data, or to like to reduce the amount of high dimensional data you have. So you kind of in the real world start with a bunch of high dimensional data, which means like some data points in some big, like 5,000 dimensional data space, and it's hard to store on a computer. So what you want to do is project that onto a smaller space using some orthogonal projection, and kind of choosing the right orthogonal space to project onto, or the right space to orthogonally project onto, is kind of the topic of singular value decomposition. And so we're not going to talk about that just yet. Let's just go over the theory of this first. So in the theory of it, what it essentially is doing is it's diagonalizing matrices that are either square and not diagonalizable, or not square and hence not diagonalizable. So it's kind of covering all the matrices that were not diagonalizable by doing a very similar thing. And so what it's doing is it's finding U, it's called sigma and V, such that A equals U sigma V transpose, where here U and V are orthogonal, and sigma is, I'll say diagonal in quotes, because A may not be necessarily square, and so it kind of is as diagonal as it can be. And so, like A may not be square. So just to give you a picture, maybe A is like not square. Maybe it looks like this. Then U and V are orthogonal. So necessarily, these are square. So that means U looks like this. Sigma is the same dimensions as A. And this is not drawn to scale. And V, let's do a different, V transpose. Looks like something like that. I'll just draw it like that. And so by diagonal, I mean it's as diagonal as it can be. And the rest are 0. Okay, so let's just go into the theory of this. So how do we do this? So to find U sigma and V, what you do is you look at A transpose, or you can look at A transpose A. And you diagonalize either one of these. Okay, so the thing is, you note that, so okay, I always forget which one to do. One of them will give you U and the other one will give you V. And let's just see if we can figure it out. Let's see. Let's see if we can figure it out, because I always forget which one's which. So A transpose should be something like U sigma V transpose times V sigma U transpose, which should be, so that will give you U. Okay. Yeah, let's look at A transpose. Okay, so the thing to note is that A transpose is symmetric. Hence, it's orthogonally diagonalizable. So you do orthogonally diagonalizable. So you orthogonally diagonalize it. A transpose is, let's say, some P, D, P transpose. And what you do is you set, so yeah, what the calculation I did before was like, if A is supposed to equal U sigma V transpose, then A transpose is supposed to equal U sigma V transpose times V, transposing each thing, and then V transpose V is the identity because it's orthogonal. So you get U sigma transpose, U transpose. And so you just set U equal to P, and D is going to be the square of sigma, right? Because this thing is, let's say, sigma 1 through sigma n, or we do R, times sigma 1, sigma R. And so you just get sigma 1 squared, sigma R squared, and then some zeros. Right, so we set P equal to U, essentially. And D, the elements of D are going to be the squares of your sigmas. So eigenvalues of A transpose, which equal the diagonal elements of D. So diagonal elements of D. We're going to set that equal to the squares of diagonal elements of sigma. So sigma I is going to be the square root of eigenvalues of A transpose. Okay, and then that gives you U and V and sigma, and then you're just going to basically solve for V by solving basically this equation, right? A VI is going to be sigma I UI, and so you can solve for this equation. So let's do an example. Let's do an example. Because that's the best way to do this. 1, 0, 0, let's do this one. Okay, so let's look at A transpose. Okay, so here's A transpose. And then we want to find eigenvalues of this. Okay, so unfortunately it's a 4x4 matrix. So this is a bad example. I'm going to change this so that it's a little easier. Let's consider, instead of this, let's consider its transpose. That way it's a 2x2 matrix, which is kind of cheating a little. All right, so let's do that now. That way we don't need to do a 4x4 matrix. Okay, this will be a little easier. 2, 0, 0, 2. Okay, so the eigenvalues are, this one's easy, lambda equals 2. And the eigenvectors are 1, 0, and 0, 1. This one's pretty easy to do. Okay, so like we're gonna set, so U is gonna be a 2x2 matrix. So maybe the first thing to do is when you write this out, you can just look at the dimensions. So U is gonna be a 2x2, sigma is gonna be a 2x4, and V transpose. So this is 2x2, this is 2x4, this has to be 4x4. In order to get, when you multiply it, you should get a 2x4 matrix. So that's just a nice thing to do so you get the dimensions right. So this is gonna be 1, 0, 0, 1. Sigma is gonna be 2x4 matrix. And the diagonal elements are gonna be the square roots of these. Okay, and then now we need to find V. So finding eigenvalues of this, so diagonalizing this, and really we didn't diagonalize. And then now we're gonna need to find V. So we need to solve AV equals U sigma. Yep. Okay, so I might need a new page. Okay, I'm just gonna copy it from last time. Are there any questions so far? Okay. So I think oh, so we don't even need to solve this. What we need to solve is we can, instead of multiplying by V, you can solve U transpose A equals sigma V transpose. Okay, so you get that so if you label these like columns, then you get root 2 V1 equals, you know, whatever this equals, and you can just find V1. This is a 2x4, this is a 4x4. This is V transpose. So I guess actually we would take the transpose of everything, and that might be easier. Let's do that. Okay, root 2 v1 equals 2 times 1, 0, 1, 0. Wasn't you the identity before? I don't think so. You was, oh shoot, you're right. I messed it up. You is 1, 0, 0, 1. That's even easier. So you get v1 and v2. Okay, but then there's still this problem of finding v3 and v4. So maybe before we do that, let's just sum up what we've done. So ui are the eigenvectors of A transpose. Sigma I are the square roots of the eigenvalues. And vi is, and sigma I vi equals A ui but then this only goes so far. We still need to find these other v, so that this only solves for some of the v's. So it's kind of a long process. And so we still need to find v3 and v4. And how do we do that? Let's see. Well, it's kind of a weird way to find v3 and v4, but these are supposed to be orthogonal. And we know v1 and v2, and so v3 and v4, we just find, we kind of find a basis for the orthogonal complement of v1 and v2. So this solves, i.e., maybe v looks like vr, and then these are question marks. And to solve for these, they need to be orthogonal to v1 through vr. So find orthogonal basis for the complement, the orthogonal complement of v1 through vr. So it's a pretty long process. Maybe we can do another example that's a little easier so that we don't need to do all these processes. Maybe I think I'll stop there for now. And if we want to do more examples, we can. Otherwise, we're going to talk about this more on Monday. We'll do more examples of SVD. Why does the rest of the vectors form a basis? So this is V needs to be an orthogonal matrix. And so this is maybe PR. And so what that means is that these columns are a collection of n orthogonal vectors, orthonormal vectors. And so, in fact, they need to form a basis for Rn. So actually, this should be orthonormal basis.